36 seconds, Europe's new rocket flew perfectly. 1 second later, both navigation computers were dead. The rocket turned hard, began to break apart, and destroyed itself. 4 scientific spacecraft disappeared with it. This was the maiden flight of Ariane 5 on June 4, 1996. The first visible failure happened at about 37 seconds after the main engine ignition sequence, but the engines had not failed first. Neither had a sensor. Investigators traced the disaster to a number inside software carried over from an older rocket, a number that no longer fitted inside the space prepared for it. The inertial reference system was still running an alignment calculation after liftoff. One part of that calculation converted a 64-bit floating point value into a 16-bit signed integer. The value represented horizontal motion. On Ariane 4, it stayed inside the expected range. Ariane 5 accelerated differently, and its horizontal value grew far larger. When the software attempted the conversion, the number was outside the protected range. An operand error was raised. The system shut down. This was not random corruption. The computer did exactly what its exception logic told it to do. The hidden mistake was assuming the new rocket could never produce that input. Ariane 5 carried 2 inertial reference systems, one active, one as backup. That sounds like redundancy, but both units used the same hardware, the same software, and the same incoming flight data. The backup was running in parallel, not waiting safely offline. It encountered the same out-of-range value and failed first. Moments later, the active unit reached the same conversion and failed in the same way. By the time the flight computer needed a backup, there was no healthy system left to switch to. Redundancy had doubled the boxes, but not the assumptions inside them. 2 computers had become one common failure mode. The failure did not leave the flight computer with a clean blank. The inertial system placed diagnostic information onto its output bus. The flight computer interpreted that bit pattern as valid attitude data. It appeared to show the rocket far from the orientation it actually had. The controller responded aggressively. The solid booster nozzles and then the main engine nozzle were commanded toward extreme deflections. The rocket veered so sharply that aerodynamic forces began tearing it apart. Electrical links between the boosters and the core were severed, and the automatic destruction system fired. A software diagnostic had crossed an interface and become a physical steering command. Why was obsolete alignment code still running in flight? On Ariane 4, it allowed a rapid restart of the countdown after a short hold. Keeping it active for roughly 50 seconds after liftoff had once been useful, and no requirement had forced that behavior to change. During Ariane 5 development, the inertial units were tested, and the flight controls software was tested. But the real inertial hardware was not included in a closed-loop test using the Ariane 5 trajectory. That missing combination mattered. When investigators later ran the failed trajectory through the actual system, they reproduced the failure. The boundary between old, trusted software and a new operational envelope had never been tested as one system. Flight 501 changed more than one conversion. The inquiry called for better exception handling, clearer separation between diagnostic and flight data, and end-to-end testing with realistic trajectories. Ariane 5 recovered. Its third test flight succeeded in 1998, and the vehicle became a long-running launch system. The enduring lesson is broader. Reused software must be requalified for the new environment. A diagnostic channel must fail safely at its interface, and redundant computers only protect a system when their failures are genuinely independent. 2 boxes can still contain one assumption. When that assumption breaks, the backup may already be gone.